Okay, today we'll be continuing our dealing with the Central Limit Theorem. The Central Limit Theorem is a very useful tool for us in the study of statistics. One of the issues that we're having at this point, though, is deciding or determining when we should use it. Well, the key is that we always refer to the Central Limit Theorem whenever we are working with sample means. If we see something in a problem about taking a sample and identifying the mean of that sample and comparing it to the population, then we are doing a problem that we should refer to the Central Limit Theorem on. Now, what the Central Limit Theorem says, and what makes it so useful, is it allows us to use the normal distribution, where we get a z-score and use the standard distribution, standard normal distribution table, like we've been doing. We're allowed to do that in working with sample means if the original variable is normally distributed to begin with, or, and this one is a big one, if the sample size is 30 or more, meaning n is greater than or equal to 30. N is the size of our sample. So if we have an n greater than or equal to 30, or if it's not greater than 30, as long as the original variable has already been normally distributed, we can refer to our standard deviation for x bar, or the standard error, as being the standard deviation of the population, sigma, being divided by the square root of n. Now, what that means is that the standard deviation is going to decrease and get smaller and smaller when we have a large sample. The larger n gets, the bigger that sample gets, the closer and closer this standard error, or the smaller and smaller the standard error becomes, excuse me. Now with that in mind, since this is the new way of working with the standard deviation, if we're going to use the Central Limit Theorem, our z-score formula changes slightly. First off, we're considering x bars, so we will be working with x bar minus mu. Mu, again, is the population mean. And x bar is the sample mean that we're worried about in the particular question that we're looking at. Let's see if I can spell sample mean. Okay. This, again, is the standard error down here on the bottom. So we'll be working with the z-score pretty much the way we've always worked with it, except now we're using x bar instead of x, and instead of just having sigma down here for our standard deviation, we have sigma divided by square root of n. And that's really the only modification that we're making to working with the normal distribution here. Okay, with all of this in mind, let's jump in and look at a few examples. First example, it's talking about heights of 18-year-old males. It says that the heights of 18-year-old males are normally distributed with a mean of 68 inches and a standard deviation of 3 inches. So on average, in the whole population, our mean of 18-year-old males is 68 inches. This should be identified already as the mean of the population, mu. Standard deviation of 3 inches, we should already be identifying that as sigma. Okay, we're talking about the population when we look at this data information. Now, we don't always know that, but we'll talk later on about some techniques you can use to find this information based on your samples. But for right now, we know that the mean of the population is 68 and the standard deviation is 3. We'll call that sigma. So part A is asking us, what is the probability that a randomly selected male has a height that is less than 67 inches? Okay, I'm looking at one person, a randomly selected male. Now, a randomly selected male does not really represent a sample. It's just one person. So in this case, we are going to use the formula for z-score that we've always used. We don't have an x bar, we just have a single value, which is x. We want to see x minus mu divided by the standard deviation. However, if you make a mistake and you use the other formula, you'll be dividing by the square root of 1. And of course, the square root of 1 gives you the same value you would have anyway. So it's okay if you make a mistake there, but this is the actual formula we should use for this problem because we haven't taken a sample. So our z-score is going to be 67 minus 68 divided by the standard deviation of 3. And of course, that's going to be negative 0.33. Well, once we have this information, we'll go to our table and we'll look up this z-score, negative 0.33. And the table will tell us that to the left of that z-score, probability that probability that z is going to be less than that would be, I guess I'll just write it out here for right now, 0.3707. Okay, so that means that the probability that x is going to be less than 67 would be 0.3707. This is the answer we're looking for. Now again, this is a problem that we've kind of already done. It's very much like a problem that we've already done, where we're just finding the z-score for that one value, and we're looking it up in the table. And the table gives us the area to the left. So if we want to know the probability that we're less than that value, it's just going to be the value from the table. Part B, though, asks us the question, what is the probability that a sample of 16 18-year-old males will have a mean that is less than 67 inches? So we're still looking to see if we can come in less than 67 inches, but now we have a sample of 16 18-year-old males. Now don't be confused by the 18, that's just their age. We have a sample size of 16, so that should tell you that we have an n equal to 16. So we're going to compute our z-score slightly different now. We're going to say z is equal to 67, which is the sample mean that we're questioning, minus 68, which is the population mean, and that's going to be divided by the standard deviation of 3 over the square root of 16. Well, the square root of 16 is 4, so we can work that out pretty easily to be 0.75 on the bottom. So we have negative 1 divided by 0.75, and of course that gives us negative 1.33. So we have a z now of negative 1.33, and we're going to look that up in the table. When we look that up in the table, we find the area to the left of that to be 0.0918. So the final answer is our probability that x bar, our sample mean, will be less than 67 is going to be equal to 0.0918. So in looking at the first value, we saw that it wasn't too uncommon to have a single person that we randomly selected be 67 inches or less. However, when we took a sample of 16 people, it becomes a lot less common to have a sample of 16 males that had a height that was less than 67 inches. It only happens about 9% of the time, whereas a single person we encountered about 37% of the time. So keep in mind that here we're looking at the mean of a group, and we would expect the mean of a group to be pretty close to what the mean of the population is. And of course, the bigger that group gets, the closer that mean is expected to be to the population mean. Okay, let's look at example 2. Distribution of salaries of police officers in the United States is skewed right with a mean of 59,000 and a standard deviation of 5,000. Now, reviewing some terms that we've talked about before, skewed right means that we have a shape that is not normal. Normal meaning normal distribution. Skewed right distributions tend to look kind of like this. They tail off to one side and they have a peak on one end and they tail off to the other, tailing off to the right in this case. So this is not normally distributed. Okay, so we have a distribution where the population is not normally distributed. That makes this a lot different than the previous problem. The previous problem, the population was already normally distributed, so we were okay. But here we have a situation where we're skewed right to begin with. So what information must we have before we're allowed to use the normal distribution? We can't use it with looking at one individual. We can't use the normal distribution because we don't have it. In order to use this, we have to go back to our rules, and I'll flip back real quickly. The rules on the CLT. We do not have original variable being normally distributed. So we must get a sample size that is 30 or more. So that would be the answer to A here, where sample size with n greater than or equal to 30. We must have this in order to use the central limit theorem. Okay? CLT is just the abbreviation for central limit theorem. Now, now that we've identified that, I'm going to go down here to part B, where it asks us this. If a sample of 100 officers is taken, what is the probability that the mean of the sample will be greater than 60,000? Well, we can see we have a sample of 100. So n is definitely greater than or equal to 30. Okay, so we're good with this aspect. N is equal to 100, actually. So we can go back now and do our z-score and find our probability of this happening by using the normal distribution. So we've got a sample of 100, and we're worried about a sample mean being greater than 60,000. So our z-score is going to be 60,000 minus mu, and mu I believe was 59,000. Okay, that's mu right there. Standard deviation of 5,000 was sigma. So we're going to apply this in our formula down here. 60,000 minus 59,000. And we're going to divide that by sigma, which is 5,000, over the square root of n, which is 100. So real quickly breaking this down, 60,000 minus 59,000 is 1,000. 5,000 over the square root of 100, which is 10. So 5,000 over 10 would be 500. So we have 1,000 divided by 500. And this is equal to 2. So that is our z, 2.00, if you like to use all the decimal places. Okay, so our z-score is 2.00. So we're going to go look, and since we want to be greater than 60,000, we're going to look up 2.00 in the table, and that gives us an area of 0.9772. But since it said greater than, we're going to subtract from 1. Because remember, the table gives us the area that's less than that. So we want to identify what is greater than by subtracting the part that's less than off, and we will get 0.0228 as the probability that X bar is greater than $60,000. And of course, this is just the way we would write it out formally. That would be our answer. Probability that X bar, or sample mean, is greater than 60,000. Okay, so going back to that question, we would not have been able to do this with looking at one person. We couldn't just take a single individual person, select them out, and test them on this scale because we have a distribution that is skewed right. But when we went down here and we had a sample of 100, we were applying the sample mean, and we could use the central limit theorem because we were working with sample means, so we could use the normal distribution because our sample size is greater than 30. All right, let's look at the next example, and this will be the last one. Coal is carried from a mine in West Virginia to a power plant in New York. And what they call hopper cars in a long train. The automatic hopper car loader is set to put 75 tons of coal into each car. The actual weights of the coal that are loaded are normally distributed with a mean of 75 tons and a standard deviation of 0.8. So we know the weights of the coal are normally distributed. Okay, so that tells us that we're good to use the central limit theorem, or we can apply the normal distribution to any example that we're looking at here. We have a mean of 75 tons. That goes for the population, so that's mu. We have a standard deviation of 0.8 tons. That is sigma. Okay, that's the population standard deviation. Now, part A is asking us what is the probability that a randomly selected car, okay, that's just one single car, will contain more than 75.5 tons of coal. Okay, so we work that out. Z is going to be 75.5 minus our mean of 75 divided by our standard deviation for the population, which is 0.8. And when you do that, that will work out to be 0.625. We'll round that off to 0.63. Remember, we have to use 2 decimal places for our z-scores. We look up 0.63 in the table, and that gives us 0.7357. So we're going to look that, or we look up 0.63. We got 0.7357, but that is the area to the left, or the area that's less than this. We want the area that's greater than. So we will say 1 minus 0.7357, and that is equal to 0.2643. So the probability that a single x, just that's one random individual, and it shouldn't be as less than, it should be as greater than 75.5, excuse me, is equal to 0.2643. That would be your final answer there. Okay, so that was the probability of working with one individual car. Now when we go down to part B, we are talking about the probability that a sample of 20 cars. So now we are dealing with a much larger group in which we've taken a sample of 20 cars chosen at random, and we want to test that their mean weight for that sample, that's x bar, would be 75.5 tons or more. So the problem changes a little bit simply because we're dealing with a sample. We are allowed to use the normal distribution because if we go back, we had the population was normally distributed to begin with. So we're okay there. So we'll use our sample z-score for our z-score for sample means, excuse me. That would be 75.5, which is the sample mean that we're testing out, minus the actual mean, which was 75. That's the mean for the population. And we want to divide that by the standard deviation, which I believe was 0.8. Yes, sorry. 0.8 over the square root of n. And in this case, n is 20. So I'll give you a second to compute that. Okay, when we do this, I get somewhere around 2.795. What we're going to do, since it's a z-score, we're going to round that to be 2.80, since we have to have 2 decimal places to use the z-score. And when we look up 2.80, we get the area 0.9974 being to the left. Well, this problem is asking us to identify probability that is more than. Okay, so since we're talking about more than, we're going to subtract that from 1. And again, that's going to be 1 minus 0.9974, which is 0.0026. Now that is a really low probability. So what we're saying here is the probability that x bar would be greater than 75.5 is equal to 0.0026, which is 0.26%, far less than even 1%. So if we compare the two, while looking at one car, we can see that one car might encounter a weight that much about 26% of the time. So it's not terribly uncommon to see in this problem one car weighing more than 75.5. But when we take a sample of 20, the probability of that whole sample having a mean of 75.5 or more would be really low. So that's 0.0026, meaning 0.26%. So that's a really low probability. So you can see that as we get a mean of a sample, we really expect that mean of the sample to be very close to the mean of the population. So we were expecting, if we took 20 cars and looked at their mean, we would expect it to be very close to this mean of 75.5. But in this case, the probability of getting it a little bit off, meaning 0.5 tons off, is very low. So we want it to be very close when we take a sample that large. Okay, hopefully this has shed a little bit more light onto central limit theorem for you. Again, you want to practice with your z-scores, knowing how to use the normal distribution table and applying the information given in a word problem to find these probabilities using the z-scores and the normal distribution table. And we're just adding on this extra aspect here of the central limit theorem, where we're working with sample means, and we have to divide our standard deviation by the square root of n. So if you have any questions, please make sure you ask them in class, and I will be coming around to talk to you soon, hopefully.